Sir John Pendry viene del Imperial College de Londres, es un físico de materia condensada, ha trabajado mucho en la ciencia de superficies, pero sus trabajos de los últimos años en fotónica y en metamateriales probablemente sean de las contribuciones más importantes de la física de materia condensada de los últimos años, y la capa de invisibilidad de la que nos va a hablar hoy probablemente sea su trabajo actual más conocido. Sir John Pendry conoce bien Donostia porque es miembro del comité científico del DIPC y también del CIC Nanogune. Su trabajo sobre metamateriales tiene que ver con la creación de propiedades nuevas. Es el diseño y la creación de materiales que puedan presentar unas propiedades que puedan sernos útiles, que sean atractivas. Simplemente mencionar también que John Pendry es uno de esos físicos que además ha creado escuela y bueno, pues algunos de sus estudiantes y colaboradores están por todo el mundo, incluyendo uno de sus primeros estudiantes de tesis, que es precisamente Pedro Miguel Echenique, presidente del DIPC, a quien ustedes conocen bien. Sin más, Sir John Pendry, por favor.
So thank you, Ricardo. Begin by saying what a pleasure it is to be back in San Sebastian again. I've visited many times, and it's always a joy to be here, particularly my association with the International Physics Center, and later with Nanogune, which I've watched grow to its present eminence over the years. So I want to talk to you today about light and how to control it. And by light, I mean all the various generalizations of light. I think Jocelyn explained yesterday how light that we see is just a very small part of the spectrum, but also part of the same phenomenon are things like the microwaves, which power your mobile phone, the light which goes into the internet, X-rays at the other end of the spectrum, of course. And all these phenomena are part of the same family that light belongs to. And controlling it is extremely important because light is very central to our lives. It's the medium through which we receive most information about the world. Think how bereft you would be if you were blind. And indeed, in the English language, to say, I see, means as much as to say, I understand. So light is very important. But what is light? Well, some years ago, in the 19th century, James Clerk Maxwell showed that light was a dance. Components of the dance are electricity and magnetism. And the change of one into the other periodically is how light progresses. So light is a dance between an electric field changing into a magnetic field, changing into an electric field. The step of the dance is what we call the wavelength, the length it takes to make that transition. And the beat of the dance is the time it takes to make the transition. So there's a beat and there's a length associated with light. And how big those are, or how small they are, dictates what sort of light, what color of light you see. Now, there are many things we might want to do to control light, many, many different ways. But we set ourselves some years ago a big, grand challenge. And the grand challenge was to make something invisible. And that was a challenge because we thought that if you could do that, you could do anything. So at the end of my talk, I hope I'll have some time to tell you a little bit about the more prosaic applications that we are already embarking upon. So what is invisibility? Well, it's not just being black, and that's a very important point. Here's Peter Pan, and I show him because he's the little boy who's lost his shadow. So even if something's black, you can still know that the thing is there because it has a shadow. And so what we need to do is to make Peter lose his shadow. And the way we're going to do that is to control light so exquisitely that it flows like water. Imagine a pebble in a stream or a rock in a stream. As the water comes near the rock, it naturally parts and flows around each side of the rock. And then, on the other side, it will close smoothly. And a little way downstream, you really don't know there's a rock in the river. Now, light doesn't do that. And so we have to be smart enough to persuade light to flow around the object, and so that we don't know that there's an object there because the light is flowing smoothly around the object, and so there is no shadow. Now, we need some help because it's going to be tough. So we're going to call on some high-powered help, and this man needs no introduction. And one of the things he showed was that light can be bent in a continuous curve. He showed that if you have a very heavy object, like the sun, which is quite heavy, or a black hole, or a galaxy which is very heavy, then it distorts the geometry of the space. And the quick 2-second lecture in general relativity, he measured that distortion of space by something you call the metric, which simply is how much a bit of space is squashed or stretched by that gravitational field. And if light is moving in a space which has been stretched, it naturally doesn't go in a straight line anymore because the space isn't straight. And so you see stars displaced in the sky if they travel near the sun. And more sensationally, and again, I think Jocelyn showed you something like this yesterday. What we have here is a red galaxy, which is very, very massive. And behind it is a blue galaxy, which you shouldn't see because it should be in the shadow of this red galaxy. But the red galaxy is bending space, and the space in turn bends the light. And this ring here is the light flowing around this central galaxy. It's not hiding this galaxy because it doesn't do exactly what we want, but it's getting there. That's the sort of thing we want to do, to make things flow around objects. Now, what we could do before all these ideas started was to make light go in a series of straight lines. So here's some light entering a piece of glass, and it refracts, as we say, at the surface of the glass and changes direction. And how much it changes its direction is determined by something we call the refractive index. And the bigger that is, the more this angle changes. But we want to be more clever than that. We want the light to go in a continuous curve. And to do that, we've got to do two things. One is to find some materials that will do the job we want, because to build anything, you've got to have a material which will build that. But the second thing we need is a protocol, which will tell us exactly what sort of material we need. Now, the materials will prove to be quite exotic, so it has been important to have some new ideas in the material science of electromagnetism. And here's the new idea, which is that if you have an ordinary material, its properties are determined by the atoms and molecules. And if you want to change its properties, what you usually do is to change the chemistry. So if you want to make glass into a very sparkling glass for a wine glass, you'll put some lead in the glass, and that makes it more refractive, and that adds to the sparkle. But there's another way you can change the properties, which until about 10 years ago hadn't been much exploited, and that is to change the internal physical structure. So we don't have to have objects as small as atoms and molecules to change the properties. We could actually engineer things like little rings of metal, and providing they were much smaller than this thing, the wavelength, then they would act as if they were rather big atoms and molecules, and so change the properties. Now, the difference between the two is that this is limited by the periodic table, but the metamaterials are limited by your imagination and how you can imagine different physical structures. I'll give you an example of a natural metamaterial. So if you take silver and polish it flat and smooth, then it's a very good mirror. It's one of the best mirrors you can have. But if you take a different form of silver, colloidal silver, which is just silver ground up into very, very little tiny nanoparticles, and you may have seen this sort of silver actually, if you have an old-fashioned black and white photographic negative, the colloidal silver is the black in the negative. And all you've done is to change the physical structure. No chemistry, just made a metamaterial. And there's all sorts of fun you can have with metamaterials. So here's a metamaterial, one of the first made by Mike Wiltshire when I was collaborating with the Marconi company. And here what we wanted to do was to make magnetism without magnets. Now, if you put, these are little copper rings, and if you put a magnetic field on them, a current will flow, and the current flows in a circle. Now, if current goes around in a circle, it in turn produces another magnetic field. So here is a circuit, which metamaterial, which will give you a magnetic response without having anything in it which is intrinsically magnetic. Copper is not intrinsically magnetic. Here's something more complicated, which is built up of lots of these metamaterial elements and copper wires. And I show you this because this particular structure is built by David Smith in San Diego. David's now at Duke University. And this has a property of having a very strange refractive index. The refractive index of this material is negative. And I'll tell you why that's strange later in the talk. This is another go at having something even more sophisticated. These guys in Berkeley, California, are making a metamaterial which has, let me see the scale here, that's 1 micron, so this is very tiny. And this metamaterial has a refractive index, but the previous one, its refractive index was relevant to microwaves. This one is near optical for the infrared. So people are making all sorts of metamaterials and doing all sorts of strange things with them. So that's the first thing. We have these new materials that can do much more than we can just with chemistry. Well, the second thing is the design criteria. And here we turn to the god of electromagnetism, James Clerk Maxwell. He was the man who showed that light consisted of electricity and magnetism. And here are his equations. Now, I don't know how many mathematicians there are in the audience, but I guess most of you wouldn't look at those equations and say, ah, yes, it's obvious that light changes direction when it comes out of glass. Anybody find that obvious? I don't. And so what we really need to do is to take this gold, which Maxwell has given us, and cast it into another way of looking at the problem. And again, the name of this new way of looking at it is transformation optics. And it goes back to Einstein. So Einstein said that gravity distorts space, and if space is distorted, that changes the direction that light travels in that space. So let's suppose that you have an ordinary flat space and light travels in a straight line. But if you have some gravity around and it pulls and stretches this space, then the light doesn't go in a straight line. And in fact, it behaves, if you sort of erect a mesh here of lines and you record where that ray of light is crossing those lines, then when you distort the space, the light behaves as though it's stuck to those lines. So you pull the light with the space like that. And remarkably, it turns out that we don't need a black hole to do that to space, or at least not as far as light is concerned, because what Einstein showed was that if you rewrite Maxwell's equations and you use his general relativity formalism to take account of the fact that space is bent or crushed, then this quantity that Einstein used to describe the crushed space, the metric, is proportional to the refractive index. It is the refractive index, essentially. So as far as light is concerned, we don't need to really change space. We just need to do the right thing to the refractive index. And Einstein's formula for the metric, which he's kind enough to give us, tells us what refractive index. So we've stolen this formula from Einstein, and all we have to do is then to say, well, what distortion of space would we like to do, and realize it as far as light is concerned by choosing the correct refractive index. So our task was to make something invisible. And what we want to do is to stop light from going through this circle here, because we want to hide something in that circle. But at the same time, we don't want to create a shadow. So it's not enough just to paint this circle black or to cover it with silver paper. So the way I do that is to cut a hole in the middle of this structure, and I squash all of space. So I push it out, but I don't push it away to infinity. I crush it inside a volume, which I'm going to call the cloak. So there's no space in here and a bit of squash space in here. And remember that if you move space, you move the light with it. So if you pushed all of the space out of here, so you push the light. But if you've been careful where you put this space, it comes spare from here, and you've not let it stray outside of this box, then if you don't move the space, you don't move the light. And so here's a more mathematical way of describing it. We're going to make this crushed region here, which is our cloak, and this is the formula for the crushing, and at the end of the day, light will flow like water. So the light will enter here, it enters the cloak, and it can't get in here because it's been pushed out of there, but it will return to where it was going before it hit this structure. And so you've made a cloak, or you've designed a cloak. Making it is another thing. The first cloak was actually made in Duke University by my friend, colleague, longtime collaborator David Smith and his group, and it was made for radar waves. But more recently, people have moved on and made cloaks for visible light. And this is a cloak which was designed by one of my postdocs and built in Birmingham. And what they realized was that in some circumstances, you don't actually need a metamaterial. So the way they made a cloak was to start with this system here with a mirror, and they wanted to make a hidden space like that. And they did it by starting with a triangle of empty space, which they then squashed uniformly vertically. And so, since you've only squashed in one direction, this makes an anisotropic material, which in fact, if you get the dimensions right, you can reproduce with a big crystal of calcite. It's a naturally occurring material. And the way they tested their cloak was, I should show you here. So if you didn't have a cloak there, this hidden region, which is covered with a mirror, would send off light in all directions. But if you cover it with a cloak, these computer simulations show that the light just produced one reflection, like a flat mirror. But they had a smarter way of showing that you had a flat mirror there, not a bent one, which was hiding something. And they looked at the alphabet through this mirror. And if you've got a bent mirror, the middle bit of the alphabet is missing. But if you put the cloak in place, if you put the calcite crystals in place, then you can see the whole alphabet because you think there isn't a kink in the middle of the mirror, and you've flattened it out. We call it hiding under the carpet. And so that was the first realization of the cloak at visible frequencies. They did this is in real color, and what they wanted to show was it works across the entire visible spectrum with only a little bit of aberration there, because there's been some argument about whether the cloak works only at one frequency. So that the target of invisibility achieved, very, very quick ride through invisibility. The been lots of papers on it, and people find it great fun. But I want to tell you before I finish about one other even stranger thing you can do. I alluded at the very beginning to something called a negative refractive index. And I'm going to remind you about something else that Einstein said that the distortion of space was a bit like a change in the refractive index. So if you squash space a bit, you make the refractive index a little bigger. But what about a negative refractive index? So this is the definition from Snell many hundreds of years ago of how glass or any other material refracts light. And the bigger this refractive index, the more this angle changes towards the normal. But if you have a material with a negative refractive index, and Veselago suggested this many years ago, then the light actually goes further and bends the opposite side of the normal. Now, just stated like that, you might think, big deal, positive, negative, schmegative, who cares? But you should care, because let's start with some empty space. Here's some empty space, and I'm going to squash this space. And as I squash it, I make it more refractive. That's what Einstein said. And I'm going to squash it really, really hard. And if I squash it infinitely strongly, then the refractive index goes to infinity. Now, if you've done any math at school, you know that a function which goes to plus infinity, if you go a little bit further and come out the other side, it goes to minus infinity and then to a negative number. So what I'm going to do is to squash space that little bit more and push it inside itself. And now I've made a piece of space which is negative, has a negative refractive index. But I've also done something very, very strange. So this is a funny sort of space, because if I take this point here and light goes past it, and then it gets the negative space, it comes back and passes the same point once and twice. So this point is passed 3 times in all. We've in fact made some space which has 3 manifolds, as we say in mathematics. The light doubles back on itself. And that has some really rather profound consequences. One of them is that you can make a lens. Now, Veselago pointed out that if you had negative refraction and you had a point of light here, then it would refocus inside this medium just by applying Snell's law. But what he didn't realize was that because he used Snell's law, which is inexact, now normal lenses can only focus to within that step of light, the wavelength. That's a very, very profound limitation in microscopy. But this result, whereby the light goes back on itself and so actually recreates what's here exactly in terms of Maxwell's equation, this way of looking at it tells you that because Maxwell's equations are an exact description of light, this focus should be perfect. And it is. And that created a great storm of excitement and not a little abuse for myself until it was verified experimentally. So that's one way of looking at it, that it's weird, a piece of negative space that Einstein might appreciate. Even black holes don't create negative space. Here's another fun way of looking at it. If you had a pool with fish in it, and you suddenly made this refractive index negative, all the fish would appear to jump out of the pond, because the light from the fish will be recreated here, and you see the fish upside down, swimming around in thin air. So that's one trick you can do with a negative refractive index, just for fun. Here's something else. Now, something else you can do is the Veselago lens was a flat lens and focus things in a line, but most lenses are curved, but you can make the Veselago lens curved using this transformation optics theory and bend the lens round until you've made a cylindrical lens. So here the blue and the green lines denote a region with a negative refractive index. And I'm going to trace some lines coming in, and they negatively refract and negatively refract. And in this particular design, this lens captures all the light which comes in from here. And there are a few paradoxes here I don't have time to explain, but if you do a computer simulation, you see all of this light hitting this big red sphere, which is much bigger than the lens, is captured inside this inner region here. What can you do with that? Well, one fun thing is to make a shadow. Now, if you have objects which are very small, they can't make shadows. Of course, the wave nature of light means that the light would just curve around that small object and would fill in any shadow. And so what you want to do is to use this, lens to make a small object appear very, very big. So if I put a small black object in here, which is less than the wavelength of light and therefore wouldn't even have a shadow, if you make it appear really big, bigger than the lens which is making it big, then it should have a big shadow. And here's a computer simulation of a black object, a lens, and this shadow region here. And here's a wave coming in from the left. You can see its wavelength here, and it creates a really big shadow. That was simulation done by Wei-Sheng Wei, one of my postdocs from Singapore. So I hope I've convinced you that negative refraction is one of the very, very weird things that transformation optics can explain and that metamaterials can realize as well. But physics, for me, is mainly about having fun. But at the end of the day, you've got to get grants from the government, and you have to pay your debt to society. And I always say that an idea, however interesting or sparkling, is going to gather dust on the shelf unless you can do something with it and do something useful. And after quite a while, metamaterials are, in fact, beginning to do something useful in the world. Now, one of the things is magnetic resonance imaging. So my colleague, Richard Sims at Imperial College, recognized the problem there. So if you want to do a very high-resolution scan of the heart, you have to pick up those little magnetic signals that tell you where everything is in the heart. You have to pick them up with a coil that's very, very close to the heart, that's inside the heart. And the way they do that is to insert a wire into a vein in your leg and push the coil up to your heart, where it collects the very tiny energy. Now, there's a problem there because you also have some very powerful radio frequency fields which can make that wire hot. And if it gets too hot, it can stick to the vein. And so it can be a dangerous procedure if that happens. And so my friend set out to solve that problem. And he said, well, why turn this exquisite magnetic signal into an electrical one? Because it's this electrical conductor which is causing the problem and getting hot. Why not build a magnetic wire? Now, there are no magnetic wires in nature, but for metamaterials, making a magnetic wire is not a problem. And so he is patenting a magnetic wire which safely gets signals out of remote regions of the body and improves the safety of magnetic resonance imaging scans. So the great thing about metamaterials and general theories of electromagnetism is that the huge range of different phenomena which we cover, right from the things which happen in an MRI machine, which are electromagnetic, to the visible, and right up to X-rays. And one of the other things which electromagnetic waves do is communicate with satellites. So if you're in a region where your cell phone, there are no cell phone masts out in Sahara Desert, let's say, then the way a reporter in the field will communicate is with a satellite communications receiver. It's a lot bigger than your cell phone. It's about 30 centimeters in diameter, and usually it's in the form of a parabolic dish, which you then point at the satellite, and it's got to have an electric motor, because it's got to track the satellite across the sky. Heavy, expensive, and consumes a lot of electricity, and it costs about $10,000. So it turns out that using metamaterials, you can make a satellite communications dish which is flat and which tracks the satellite electronically. Of course, metamaterials can be tuned very cheaply, and you can make a satellite communications receiver like that. And there's a company called Meta for metamaterials, which is 50% funded by Bill Gates, I believe. And this is a picture of it. It's about 15 by 15 centimeters, and they're hoping to market it for about $2,000, which is a lot cheaper than the conventional satellite communications receiver, and it takes very little power. You can power it from the USB socket of your laptop. So that might greatly expand the market for satellite communications. And in fact, already, Toyota have signed a deal with Meta to incorporate one of these flat SATCOMS receivers into the roof of their cars. And the idea is that they want to be in constant communication with their vehicles in real time. And there was a test drive across America from, I think, San Francisco to Washington of one of these vehicles calling in at the Detroit Motor Show, which was a prototype of what Toyota is going to do to your car when they get this thing up and running. Now, there are many other things I could show you, but there's just one last thing. Federico Capasso invented a source of terahertz radiation. This is the sort of radiation you use in these active cruise controls in cars. It's a short-range radar which sees where the cars are in front. It's also used in security at the airport. These are the things which sort of physically undress you when you go through the scanners and see whether you're carrying a weapon. So it's quite an important source of radiation. And he invented something called the quantum cascade laser. And the problem there is getting this quite long wavelength terahertz radiation out of this very tiny piece of electronics. And it can be done, but Federico is including metamaterials in his structures so that you can more efficiently extract the terahertz radiation. So my time is up, but I hope I've shown you that the sort of physics we're doing with electromagnetism is new, it's fun, it has a lot of surprises in it, cloaks and negative space and three manifolds, but at the same time, it drives forward to products which are going to earn its way in the world. Thank you for your attention.